Hello, I am Shubhrata Bharati. I am presenting a paper in 20th International Conference on Intelligent Systems Design and Applications. The paper name is Optimized NASNet for Diagnosis of COVID-19 from Launch City Images. My paper ID is 85. This is the outline of the presentation. Deep learning has potential in the diagnosis of novel coronavirus disease. Nevertheless, the effectiveness of deep learning models varies when applied to defined datasets and cross datasets. This paper proposes optimized neural architecture search network NASNet for COVID-19 diagnosis. Two forms of NASNet models, namely NASNet Mobile and NASNet Large, are applied to a dataset of 3,411 computed tomography launch images freely available on GitHub repository. For the experimentation, 85% of the total samples are used for training, while the remaining are used for testing. The training and testing losses and the classification accuracies are varied with respect to the number of epochs. Actually, deep learning since December 2019, the novel coronavirus disease caused by SARS-CoV-2 has spread all over the world and has become a global pandemic. In many countries, the suspected patients of COVID-19 are increasing day by day. As a result, automated detection of COVID-19 is being considered for managing this infectious disease. Therefore, analysis of the launch CT or X-ray scan images is highly demanded for a quick identification of COVID-19. CT images are reported to have high sensitivity than X-ray images on account of the potential use of CT images. Hospitals of the overloaded patients can conduct CT images for rapid diagnosis of COVID-19 patients and for considering treatments according to the symptoms of patients. CT images play a crucial role in the diagnosis of lung diseases. This is some research works uh, and they have already, for example, BGG 16, BGG 19, SNet 50, V2, TestNet 21, Dark Coveted, CovXNet, Coronet, etc. Algorithm have been proposed by various researchers in order to detect COVID-19 from the CT images or X-ray images. The main contributions of this paper are as follows. The NASNet is proposed for applying to CT images for analysis of COVID-19, where NASNet is optimized by hyperparameter tuning and considering data augmentation. The effectiveness of NASNet mobile and NASNet large algorithms are evaluated in classifying COVID-19 and non-COVID-19 patients. In this architecture, actually, if this architecture consists of 771 layers and 2 nodes. It is designed by a lot of parameters, where trainable parameters are 8 lakh 5 where different types of parameters such as trainable parameters and non-trainable parameters. NASNet large and NASNet mobile architecture have input image sizes of 331 by 331 and 224 by 224 correspondingly. Okay. Table 2. This table mainly presents the values of accuracy and AUC for each epoch for NASNet mobile and NASNet mobile algorithm. The total images for the experiment were 3,411, where 85% of the samples are for training and 50% for testing. That means 2,899 were training images and 512 were testing images. In the training images, we detected 1,458 of positive cases and 1,441 of negative cases. On the contrary, 268 patients were COVID-19 positive and 244 patients were COVID-19 negative in the testing images. This is the performance of NASNet large algorithm, where accuracy and AUC values are calculated and evaluated for training and testing images for 15 epoch. Okay. These figures show that this is figure 2, mainly this type of figures. NASNet mobile A depices NASNet mobile algorithm and B depices NASNet large algorithm. Okay, these figures mainly illustrate that the epochs versus loss, including training and testing loss for NASNet mobile and NASNet large respectively. These figures also show that the training loss is decreasing while the number of epochs is increasing. However, the testing loss curves have several increments and decrements with increase in epochs. Nevertheless, the testing loss at an epoch 15 is lower than that 0. These figures show that the bar diagrams of NASNet mobile and NASNet large respectively in order to compare the accuracy against the number of epochs. The testing accuracy values vary. The testing accuracy values vary with the increment of epochs. However, the testing accuracy at an epoch 15 is higher than that of 0. Consequently, it is likely that if we use a large number of epochs, the loss will be low and the accuracy will be high. Table 4 illustrates the elements of the confusion matrix. There are 4 elements in the confusion matrix: TP, FP, TN, and FN. TP means true positive, FP means false positive, TN means true negative, FN means false negative. These tables mainly presents the performance result of for NASNet. From the below table, an accuracy of 82.42% and a recall of 78.16%, a precision of 92.16%, and an FN score uh, of an F1 score of 84.59% are observed for NASNet mobile, whereas an accuracy of 81.06%, a recall of 84.43%, a precision of 84.33%, and an F1 score of 82.33% are found for NASNet large. It is clear that the values of accuracy, F1 score, and precision for NASNet mobile are larger than the values of NASNet large. On the contrary, only the value of recall for NASNet mobile is less than the NASNet large. This figure mainly illustrates the AUC and ROC of NASNet mobile and NASNet large. The ROC plots display the false positive and true positive rates for binary classification in our proposed work, while 0 indicates non-COVID-19 and 1 indicates COVID-19 patients. The AUC values of non-COVID-19 and COVID-19 patients for the case of NASNet mobile are 91%, that is close to the value of 1 means 100%. Therefore, NASNet mobile properly classifies the patients against NASNet large. Conversely, the AOC values of non-COVID-19 and COVID-19 patients are 0.89 for NASNet large. Consequently, NASNet mobile provides more valid results than NASNet large for CT images. This is the comparative analysis section. The papers of 8, 10, 9 and 10 research had a limitation that they use their proportional algorithms for a small number of CT images. The authors of 11, 13 to 16 use different deep learning algorithms for X images. Therefore, fair comparisons are not possible in terms of performance metrics of accuracy, recall, use, etc. Instead, NASNet algorithm is found to be quicker and simpler compared to other deep learning algorithms. In our proposed work, we have used a large number of CT images and applied a novel optimized NASNet mobile and NASNet large algorithm for classification of non-COVID-19 and COVID-19 patients. Now I can conclude the paper. This work proposes NASNet deep learning algorithm for detection of COVID-19 employing CT scan images. Experiments are done for the case of 3,411 CT scan images where 85% of the samples are used. It is shown here that NASNet mobile outperforms NASNet large in terms of accuracy, precision, AUC values in the diagnosis of COVID-19 for the cases considered for an epoch of 15. NASNet mobile obtained a classification accuracy of 82.42% and an AUC value of 91%. However, the results will vary for different datasets and for cross datasets. Hence, more research is needed to investigate the effectiveness of NASNet.